So let's finish off our discussion of work and energy, and we'll look at a couple discussion of chemical energy, looking at the unit of energy of calories, and then do some examples. So as you've noticed, there's a bunch of units relating to energy. Of course, energy is so important. And so let's just go through a couple of them. So the first two are unfortunate, in fact, that it's the same word. And so we have a calorie with lowercase c and calorie with uppercase c. And so they're related to each other. Basically, uppercase c is 1,000 times more. But the one that we sort of know as calories and things that we eat is this one here, kilocalories. This is the one that we'll use primarily. And so we've got a sort of a pretty simple equivalence here, that 1 kilocalorie, again, capital C, but we'll often use KCAL just to distinguish it from this guy over here, is 4,184 joules. And so we'll use this. This is a really key one because it's sort of helpful to get sort of a feel for energy that we might use in our everyday lives, and we'll get to that. Another popular one that we'll see is the British thermal unit, BTU, and so this is essentially equal to 1,055 joules. Again, our physics variable or unit is the joule. And what this is it's the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. And so that's kind of a standard that people will use. And then, and just by the same token, right, the calorie is the amount of energy needed to raise 1 kilogram of water 1 degree Celsius. And so it's basically the difference between, again, these calories, which are more SI, unit system international, and then the BTU, which is more the British system, which is what they use in England and what we'll often use here. And then, as we've mentioned, there's the kilowatt hour that we've discussed as well. And so, and of course, we've mentioned that this kilowatt hour is kind of a wonky unit. And so let's try to look at this a little bit closer. And so I'm going to try to find out how much energy in joules we have with a kilowatt hour, to try to sort of unpack this. And so 1 kilowatt hour. And so let's sort of expand this. What does that mean? Well, a kilo means 1,000, so it's 1,000 watts. A watt is a joule per second, and then an hour. And so you see here, I can not really think of many other examples of when we do this in science, but we have the time on the top and the bottom, so in some sense it cancels out, but it's in different units. Here's an hour versus a second. And so it's a little bit of a pain to convert this into pure joules. But hopefully that idea that time part cancels sort of leads you to this idea that this really is a measure of energy itself, even though it's really confusing. And so what I'm going to do is just start with this and just do some of our unit conversions. And so my goal is going to be to change this hour into seconds. And so I'll start by using our relationship that we know. 60 minutes is 1 hour. And so when I do that, I cancel the hours. And so now when I multiply that through, I'll have units of joules times minutes per second. Still not great, but heading in the right direction. And then I'll use another conversion, which is 60 seconds in 1 minute. And so the minutes cancel. And then we see here that these seconds cancel as well. And so when I go through and multiply this all the way out, I'll get units of just joules. And this is where we get this number, 3,600,000 joules. And so often we'll write that as 3.6 megajoules. Just wanted to go through that one again because that is such a weird unit itself. Again, kilowatt hour, it's just easier for us to build it that way, and is a measure of total energy, not of a power. Okay, so then we've talked a little bit about heat energy, right? So hot things have more energy than cold things, and heat, really is just the kinetic energy on the microscopic scale. So it's the vibration and fast motion of individual atoms and molecules. And just a note, so even though it's kinetic energy, it's generally hard to derive useful work out of it because the motions are kind of random. But anyway, it's definitely an energy that we'll use quite a bit. And then typically, again, what we'll do to kind of put it into terms that help us make more sense is we'll oftentimes try to put these things into like the calorie. which again, when we write capital C calorie, what we'll tend to do is write it as a kilocalorie. And so that leads us to chemical energy, right? And this is this idea that when groups of atoms come together to form different chemical compounds, right, they store energy in these chemical bonds, these electrical bonds that keep them together. And rearranging these bonds can release energy. And this, sort of in broader context is basically, what chemistry is, sort of the study of how these different bonds work. And so for us, though, we can look at different types of things and sort of understand sort of how much energy can be released from them. So just some sort of examples. And so we'll start with sort of a simple one. Burning a wooden match releases about 1 BTU, or again about 1055 joules. And so what we will like to do is for different materials is express them in kilocalorie per gram. So that tells you how much energy is in each unit of mass for that particular item. And so, for instance, for this burning match, we can just kind of use these numbers that we got here. So again, we're talking about 1055 joules. And so if I take that, so if I take 1055 joules and then divide by the grams, and so we're going to say that typical match is about 0.3 grams. When I did that, I got roughly 3,500 joules per gram. And so that's good. But again, what we like to do is put it into calories, because that's the kind of thing that makes more sense to human beings. And so I'm going to take that and then multiply by the fact that we know that 1 calorie, which again we'll call kilocalorie, is the equivalent to 4,184 joules. And when I did that myself, I got about 0.8 kilocalories per gram. And so again, that's roughly 1 kilocalorie per gram. And that lets us know sort of how much energy we can release from this chemical reaction. That's what burning a match is, per mass of that particular material. And so this gives us the way to kind of compare things. And so here we've got just a little bit of a list. And so burning coal, again, so that's going to have more energy per gram, 8 kilocalories per gram. Gasoline, which ends up being one of the best that we have, right, which we'll talk about later, comes out to be about 11.5 kilocalories per gram. And this is sort of like our sort of getting near the top as far as chemical reactions go. There's very few substances that will give that more than that of energy per gram. And so for food, right, this is really key to us, right? We get the energy to do things out of food, and this is basically the chemical energy in these bonds is where we're getting this from. And it works out that you can look at the different things we ingest. So again, carbohydrates, proteins, and fats. And so we like to put them into this kilocalories per gram. So a carbohydrate, you get about 4 kilocalories per gram. Protein, 4. And then for fats, you get 9 kilocalories, which is getting, again, close to that gasoline number, which again is about 11.5 kilocalories per gram. And so that's how much energy we can ingest from these different items. So it's actually, getting, the same order of magnitude roughly as, like, say, gasoline is. And so you can actually look at your chart. So here's one of these charts we have in the back of all of our food, right? And what does it tell you? Well, it tells you, how much fat you have, how much carbohydrates, and then how much protein. So again, we got the protein, carbohydrates, and fat. And so we can look over here and again use these ratios we just talked about. So for each gram of fat, you've got 9 kilocalories per gram. And so in this particular case, I'm going to multiply this by 8 grams. And when I did that, I came out with about 72 kilocalories. For the carbs, we're going to use so 4 kilocalories per gram. In this case, in this particular item, we have 12 grams of carbohydrates. And so by my calculations, that gives us about 48 kilocalories. And then the protein, we got 4 times about 8 grams, which gives us 32 kilocalories. And then when we add this all up, we get that number that's actually pretty close to what they're saying. And so for each serving of this milk, each glass of milk, we've got about 152 calories, which again, for us scientists, we want to call it kilocalories, just to be kind of careful there. But kind of cool. You can actually, sit down and look at this thing on the back of your food and kind of understand it hopefully a little bit better. And so that's how much energy we get from the chemical reactions for these particular types of food products. And so then what we can do is kind of convert this, say something, okay, how much can you do, with a glass of milk consisting of 152 kilocalories? And so, for instance, in this case, so let's look at this. So we take, again, 152 kilocalories, and then what I'm going to do is convert this into joules. So I'll sort of do the opposite of what we've been doing. And so I'll write it out, that 4184 joules per 1 kilocalorie. And so that's going to give me, when I figure this out, I got 6.35 times 10 to the 5th joules. And so one way you can write that is 635 kilojoules. And so again, this is the number that we use sort of talking about, more informally, how many calories is in that sandwich, in that glass of milk, whatever. This is the number, though, that we're going to need to use to look at different types of physics quantities in general. And so now, like, what we can do is, one thing we can do is take this and equal it to gravitational potential energy. And so take this 635 joules, not kilocalories, beg your pardon, and then take that and figure out, sort of basically, using this particular, energy that we get from a glass of milk, how high can we go? And so we'll divide this by m and g. And again, so for g, in this class, we've been using 10 meters per second squared, so I'll write that in there. And I keep writing kilocalories, but as we know, it's kilojoules, pardon me. And then for the mass, I'm just going to use, just to make the math work out a little bit easier, 63.5 kilograms, which is somewhere in the neighborhood of 140 pounds, maybe like the average mass that we might have of a person in our class. And so what's nice is it makes this math a little bit easier. Here, this cancels out. And so when I divided this here, I got about 1,000 meters. So roughly a glass of milk, if you just convert that straight into gravitational potential energy, which of course is hard to do, right, basically gives you the energy to march yourself up 1,000 meters up a mountainside or something like that. Just kind of give you a sense of what this stuff can actually physically do for you. And then one last thing, just again to kind of get better at some of these calculations, let's look at the typical diet. So a typical human diet, we're told is about 2,000 to 2,500 kilocalories a day. And so I'll take the smaller of those, why not? So 2,000 kilocalories. And so what are we actually looking at here? Well, so that's the kilocalories, and again, I'll use my conversion factor to go back and forth. This is key. And when I multiply this out, again, you get something like 8,368 joules, right? And so this is, the main reason we keep things in kilocalories, is when you actually look at the joules, it turns out to be quite a lot. Now, this is a huge number, but what we like to do is just sort of break it down. And so here, I'll write this as 8.37 megajoules, okay? And one thing that's kind of interesting is to look at, then what is the power output of a human being? And so what is power? Well, it's energy divided by time. And so in this case, it's going to be 8.37 megajoules divided by 24 hours. Now, to get this into watts, what we're going to want to do is convert hours into seconds. And so that's something that we've done before. And so we know that 1 hour is 3,600 seconds. And so the hours will cancel, and we'll get megajoules divided by seconds. And when I did this, I got 96.8 joules per second. So about 97 So this is, let's just round up, 97 watts. And so that's the energy output of a human being, again, just assuming this sort of regular diet here. And if you look at this chart we sort of looked at yesterday or last time, so here would be that output. So for the 2,000 kilocalories a day, 97 watts. Now for a larger human or someone that's maybe doing more, you can go up to like 145 watts. But again, we can kind of put it then in sort of reference of, how much energy do we use versus like a flat panel TV or something like that. All right, thanks.